Okay, so just one of the list point. The next two points. The next exercise sheet will go out probably at the end of the weekend. So please take a look at that. If you haven't handed in your exercise sheet 2 yet, please do. Maybe deadlines is something to aim for, not very hard and fast rule, but I would like them back by the end of the year at least. So there's something to aim for. The next one will go up. There'll probably be one after that. There's one more after that. So we'll have 4 exercise weeks. Then there will be a take-home exam and an oral exam after that. And that will be the total. Then we can wait the exercise sheets versus oral exam versus final exam, so that it comes out in your favor. But we can discuss that later. Okay. I am aware that there are audio issues with the YouTube recorded lectures. I have ordered a panel mic. So the last 10 lectures want to have better audio. Has arrived. So again, I am aware of it. I will correct it. So hopefully the last lectures will have a better audio. Okay. Good. Okay. So. All right, so today I want to start what will likely take me 2 lectures, and this is a really important aspect of formal field theory, which is that remember what we're trying to do here is we're trying to use representations of conformal algebra to organize formal field theory in some sensible way that will allow us to do physics. Okay. Fortunately for us, there's a fair amount of representation theory that is known that we're basically using, and a lot of it comes from analogy, direct analogy with what goes on with angular momentum in quantum mechanics. This is because angular momentum in quantum mechanics is essentially the group theory of the SOV special orthogonal 3x3 matrices. Special, remember, means determinant of the matrices equal to 1. And what we're doing is, we said that basically we can take our SOP equal to a formal group and map it to SO D plus 2. And this will allow us to use what we know about the set of orthogonal matrices of unit determinant to say something about the conformal. Right. So we're using the representation of the representation theory of SOT to say things about the representations of the conformal group. And this is actually quite a useful thing to do because we know a lot about these types of matrices. Okay. And again, if you set D equal to 3, then SOT is the group theory that governs angular momentum in quantum mechanics. Right. I'm sure you have already, but if you haven't, really a lot of really interesting things can be learned about quantum mechanics by studying angular momentum operators. So it's not just about solving Schrödinger equations, there's a lot of really rich mathematics as well. And we're drawing on this really rich mathematics because this is okay with okay. So what I want to do here today is start off this little story about how we can use unitarity. Unitarity means I have some set of state, and again, we talk about the formal field theories, states are the famous operators in the theory. So I have some set of states or operators. Let's focus on state, and I want to demand that those states, which are vectors in some Hilbert space, have positive norm. And so positive norm, well, in this case, non-negative norm. If I have a negative norm for a particular vector in this space, then Information is not conserved in that theory, and we say that unitarity is violated. Right, so we're going to demand that unitarity not be violated in the theory, which will put a constraint on the positivity of the norm of these vectors. And we're going to use that positivity of the norm of the vectors to bound the scaling dimension of these operators. Right. So we're going to see that not all scaling dimensions are allowed. Okay, scaling dimensions, remember, was the eigenvalues of the dilatation operator. So not all eigenvalues are allowed. We'll find that those eigenvalues are bounded, and I'll give you a general statement for the bound of the eigenvalues, and then I'll pick some example. Actually, computing the bound, knowing the bound is one thing. Actually, computing it for a specific theory is quite another. It's not trivial. But I will write down some of the bounds of some theories like free conformal field theory, and I'll tell you that we can use this to organize the states of operators in the theory. And in fact, we're going to make a much stronger statement. We're going to make a statement that there are a unique set of operators that have this bound of their scaling dimension. And once I know those operators, everything else follows. But that's quite a big statement. If you think about a quantum field theory, what I'm saying is that there's some fixed set of states that if I know those states, in fact, I know everything about that theory, right? In a conformal field theory. In a general quantum field theory, this is not true, right? I can write down fields, I can write down operators in the Lagrangian, and I have to solve differential equations for these things with some specific conditions. In a conformal field theory, it's so rigidly fixed by symmetry in the theory that this is no longer the case. That there are some fixed set of operators, and once you know those operators, you know everything about that theory. Because these are quantum theories, when I say everything about that theory, I don't just mean the values of those fields, I mean all their correlation functions, all of their correlation functions. Okay? So I don't know if you guys are familiar with this with the breakthrough prizes. You heard of this? Okay, so the breakthrough prizes were awarded yesterday, or the day before maybe, for 2023. And the breakthrough prize in physics was actually awarded to two people whose primary contributions come in conformal field theory. So essentially, the breakthrough prize for this year was awarded for conformal field theory. They were awarded to John Riccardi, who's a professor at Oxford, who's given enormous developments to conformal field theory, specifically in the context of statistical mechanics, but also more generally in quantum field theory, and to such a general as logic. And there's a paper, the critical paper in conformal field theory is a paper by Zamolodchikov, Ellerman, and Polyakov. And it's called the BBC paper. So Ellerman, Polyakov, and Zamolodchikov. And what they did was show that once you know primary operators in the conformal field theory, you can solve the conformal field theory. So that's what the breakthrough prize was doing for this year. Right? So we're not studying irrelevant things. Okay. So okay. So I want to show, we want to demonstrate that the scaling dimension of operators in conformal field theory are bound. Okay, bound from below. So to do that, we're going to start by recalling a couple of things. I'm going to try and draw a logical line of reasoning here. So follow me on this, and please do ask questions if some of the logic is not there. So first point to note is that in radial quantization, if I spent a little bit of time making a fuss about how we conjugate things in radial quantization. Well, here's where that conjugation comes into play. The first thing is, if I take the dimensional operator, and I take the radial conjugate of this, so this was, remember, this was the Euclidean dagger operation, right? So the Euclidean conjugation operator. P nu conjugates to K nu, the generator of special performance transformations. Similarly, K nu conjugates E, and the dilatation generator is anti-cell conjugate. So that this conjugates minus E. Okay. That's point number one. Point number two that we need to keep in mind is by the formal algebra, the commutator of K mu with P nu is just I times 2 delta mu nu minus 2 times the generator of Lorentz conjugate. Okay. And then point number three is that by the state operator correspondence, anything that I say states, any bound we derive for states will also hold for operators. So by the state operator correspondence, any bounds that we derive for states also hold for operators. So which one was easiest for us? That's going to be states. So these are points to keep in mind. Now I want to make an assumption. So let's suppose that there is such a low bound of the dimension, on the scaling dimension of some collection of states, let's say psi. Right. At this point, this low bound could well be minus infinity. We don't know this. We don't know any better, right? Suppose there is such a low bound. Let's call it epsilon naught. So assume that epsilon naught is the lower bound on the scaling dimension of some collection set of states in other words, I have some set of states psi labeled by some number I could go from 1 to whatever. And if I act on these guys with I times the dilatation operator D, then I'll get epsilon naught times these states, right? So the epsilon naught is the eigenvalue of the dilatation operator D acting on these states. Some set of states. Don't know how big the set is, but I don't really care. However, I am going to assume that the set of states is normalized, right? So I'm going to assume that psi I in a product with psi j standard in a product of my given space is delta I j. You can not normalize, I can always use your normalize it, also normalize there. Yeah, so I'm not using any generality there. Then, by definition, this statement is a statement that I times the dilatation operator acting on psi I, all of psi i's is just epsilon naught times psi I. And that's what it means to say that this is a low bound. Well, this is what it means to say that this scaling dimension of these states. Okay. This could well be minus infinity, but we'll see that it's not. And these set of states will spell out some spin off of it. That means that I can collect them all into some set that has the same experiment. Now, so I've explained to you what it means for this to be for epsilon naught to be a scaling dimension of these states. What does it mean for it to be the lowest scaling dimension? Well, one of the things that we learned in the last lecture, where I left you off the last lecture, is that this guy Ku acts like a lowering operator, like a ladder operator, the A&E dagger and the harmonic oscillator. Ku and Pu play that role in this story, with Ku being the lowering operator. So what Ku does is Ku will act on some state to lower its scaling dimension by 1. Well, if these set of states have low scaling dimension epsilon naught, that means that Ku acts on these states to annihilate those states. So epsilon naught is the smallest scaling dimension. If Ku acting on psi I, all of the psi i's, is 0. So now we know what epsilon, what it means to say that epsilon is a scaling dimension, and we also know what it means to say that epsilon is the lowest scaling dimension. Right. So now what we want to do is ask if this guy really is minus infinity, or is there some smallest value that's not minus infinity. So with that end, what I want to do is consider the states that I get by acting on this with the raising operator, P's, right? And I'm just going to consider some linear combination of these states. So consider the state of phi. I get, I'm taking some linear combination over, let's say, nu of some set of coefficients a nu with the raising operator E acting on this phi. Okay. And I want to demand that the norm of this state, right, be non-negative. Now, if you think about it, these are the states that are going to live in my conformal field theory. Okay, all the states in conformal field theory are going to be of this form. In the same sense that all the states in the Fock space of the harmonic oscillator of the form, the raising operator acting on the ground state. Those are all the exciting states. So this way is that. So I'm going to require that phi, let me pull out phi be greater than or equal to 0. So it'd be non-negative norm. If these states are negatively normed, then my conformal field theory is non-unitary. And non-unitary means that I'm losing information in the system. Okay? And generally we believe that non-unitarity is bad. So when I say that we're talking about unitarity bounds, that's what I mean. So this means that we require that So taking the definition of this, recalling that when I conjugate this to make bra phi, I have to conjugate this with the Euclidean conjugation, and if I conjugate p, I get k. So this means that I require that psi I k mu sorry, this phi in a product of phi is the sum over, let's say, mu and nu. When I conjugate the a's, these are just numbers, but when I conjugate them, I'm taking complex functions. So this would be something like a nu star a nu, and then I conjugate this side psi I. If I conjugate the p, I get k nu, and then I have the p nu from here. Psi I, and I require that this thing be non-negative for all the coefficients a and a, which means that this guy in here must be non-negative. So let's call this 2, 3 holds for all a mu, if and only if the matrix a mu nu, which for some fixed phi I is this guy, is does not have any negative eigenvalues. So we translate this bound on the norm phi into a statement about linear algebra at this matrix. Right? So this is a statement from linear algebra. You can check for yourself. What is this matrix exactly? Note the following. Because the KUs annihilate these states, if temporal are not of the lower bound, I can replace this product with a commutator. You see that? Right? Because a mu, or a mu, is psi I, k mu, p mu, psi I, minus psi I, p mu, k mu, psi I. And this is 0 because of that relation up there. So I'm not doing anything, I'm starting at 0. But this is just the same as psi I, the commutator of k mu p psi I. Now you know why I wrote that down. So I can replace the commutator inside there with this expression again. I and psi I times 2 delta mu. Sorry. The rotation operator minus 2 times m nu, all acting on this is just 2 delta mu by I and I d psi I minus plus 2 psi I and minus I m mu psi I. Well, this is just epsilon naught psi I, and psi I is normalized, so that's just 2 epsilon naught delta mu plus 2 times psi I minus I and mu. So, in order to ensure that that matrix A mu nu has no negative eigenvalues, we need to make sure that this guy, this expression here, has no eigenvalue that's smaller than minus epsilon naught. Okay. So once we find the smallest eigenvalue, we'll put some bar on epsilon naught. So we need to think about what's going on there. So what we want to do is find the smallest eigenvalue of this matrix. Okay. So what is smallest eigenvalue? Right. So in order to find this smallest eigenvalue, we're going to play a little trick. Now, to rewrite this matrix I mu nu in a particular way. So to find smallest eigenvalue, we rewrite minus I m mu nu in the following way. Firstly, I'm going to take 2 copies of this guy. So that's equal to a half times minus I times. Now I'm going to calculate the indices of delta mu alpha, delta mu beta, minus delta mu beta, delta mu alpha times m alpha beta. But I haven't actually done anything here. Think about the way the Kronecker delta acts on this. It says you identify A, the alpha, you replace it with mu, you identify the beta, you replace it with mu, that's because I sum over repeated frequencies, right? So basically, I'll get 1 from here and then 1 from here. And then the factor for half counts for the account. This is an antisymmetric matrix, right? So the factor for half will count for the factor of 2 that comes out of it. So all of that is rearranged like this. What does this ball mean? Well, what it's ball mean is that if I define a new object, V, way that I'm going to do this now, then I can write this product as V dot M in U, where the matrix B, the antisymmetric matrix B, alpha beta, has unique components minus I delta U alpha delta U beta minus delta U beta delta U alpha. Right. Each of these V alpha betas is a matrix in its own right with a row index U and column index U. Okay. All in all, in d dimensions, there are half d times d minus one of these values because they are antisymmetric matrices. Okay, so there are half d times d minus one such matrices. We are beta. But what are they? I've just used them to define this. I've just rewritten this empty and used in this funky way. But is there any interpretation that I can assign to this? The answer is yes, and that's because these satisfy the following relation. Take this yourself by actually just substituting directly into what I'm about to write down. But they satisfy the relation that B alpha beta commutated with B rho sigma is I delta rho delta beta rho delta alpha sigma minus I delta alpha rho delta beta sigma minus I delta beta sigma delta alpha rho plus I delta alpha sigma delta beta rho. Let me ask you, what is that?
Computation relations.
What are
It's so one. Lowering, combination of how you now.
yeah, the delta very important. If the betas,
Yeah, it's one, but they're not us, so it's.
so it's utility. Okay, so anyone?
The ones you do accessible.
Good. If alpha and beta went from 1 to 4, then it would be equal to 4.
So then alpha, it's a D.
The V alpha betas are nothing but the vector representation, the generator of the vector representation of f of d. The generators of the vector representation of the S of d. That's cool because I know lots most things about FOD. I need to make one more elaboration, which is, why am I calling this a dot product? Why am I writing this as a dot? Well, the reason is because I can actually call it as a proper dot product. So let me elaborate a little bit on this dot product, or playing with the dot product. So suppose, okay, in our picture here, V and M are not any two objects. Right? They're certainly not vector objects. Right? What they are two antisymmetric matrices. Right? A more mathematical way of saying this is that they are rank two antisymmetric tensors. Okay, so suppose A and B are rank two anti-symmetric tensors. Anybody want to tell me what else you might call them? Q-balls. Well, then we have rank two antisymmetric tensors, or in other words, Q-balls. Then what we've done here is define A dot B as 1/2 A 1/2 of the sum over mu and E alpha beta. Sum over alpha beta A alpha beta B alpha beta. Notice the summation expression. Okay. So let me do an example to illustrate what this means. The example I will use is SOP. Okay, alpha and beta will run from 1 to 3, and A dot B because A1 2 B1 2 plus A2 3 B2 3 plus A3 1 B3 1. That's what that sound means, right? The reason I know there's a 3 is because if D equals 3, then the algorithm tells us that I can always swap out these indices over an antisymmetric object for the vector index. So in dimensions, we can always swap out an object that is antisymmetric into indices using the rule that AI, only one index now, is half epsilon I j k, which is a completely antisymmetric rank 3 tensor. A j k. Okay. On the right hand side, you have a rank 2 antisymmetric tensor. On the left hand side, you have a vector. Explicitly, this means that I can define A1 as A23, A2 as A1, and A3 as A1, 2. Okay, and similarly for B. Well, what that means is that this sum here A12 plus A23 B23 plus A B1 B1 is just A1 B1 plus A2 B2 plus A3 B3, which is what we otherwise call the vector A dot vector B. Right, so this product that we're defining is actually, honest to God, dot product, right, which I can then generalize to higher dimensions using forms. But in 3 dimensions, I can make the population explicitly. Right? This is exactly right. Good. So there's a fair amount of math in here that seems quite abstract, right? We're just filling out representation, we're working on group theory and the algebraic structure. But actually, you know, if you've done a first course in quantum mechanics, believe it or not, you've actually seen all of this math before. You might not have phrased it in this way, but I promise you, you've seen it before. If you've seen the things that you do in quantum mechanics, then you know this. And as such, there's actually quite a nice intuitive way to see that these B alpha betas are the generators of SOD. At least it's nice and intuitive for the case D equals 3. So get some intuition for why the alpha beta generates SOD. Let's consider rotations in 3 dimensions. And in particular, I want to think rotations. Okay, so if I have 3 directions, all 1, 2, and 3, I want to make a rotation about the 1 axis. I want to make a rotation in the 2D plane. Okay. So let's consider the 3 and rotations in the 2D plane. Right. So here we write down an explicit matrix that accomplishes the rotation by theta in the 2D plane. This looks like 1, 0, 0, 0, 0, cos theta, sin theta, minus sin theta. Yeah. Okay. This is something that you've already seen, since first year. So now I need the following statement. The representation, this representation of S of P is a three-dimensional representation. It's a 3 by 3 matrix. Okay. So this representation is three-dimensional. One. This rep of S of P is that. Now, I need to be clear about something. The representation of the group, okay, need not be these two threes need not be the same. I can find a two-dimensional representation of this group. I can find a seven-dimensional representation of the group. Okay. The size of this matrix in this case happens to be 3 by 3, but it need not be. Right? As long as the matrix I find, or the operation I find, it will be differential operators. As long as it satisfies the appropriate algebra, that's it. It furnishes the representation. But it can be whatever you want. Okay. So in this case, that would be 3 by 3 matrices, which means that this representation is a three-dimensional representation of S3. Okay. The second point is that the vector representation of SOD is a d-dimensional representation. This is a statement from abstract algebra. Okay. Statement 2. The vector representation of SOD is d-dimensional. Then statement 3 is that there is a unique d-dimensional representation of SOD. And taken together, these three steps means that this must be the vector representation of SOD. Yeah. Okay. So it follows that. So now we can work on, should we go to infinitesimal transformation? So if I go to infinitesimal rotations, then I can express this guy where I'm choosing theta to be small, much less than 1. If I choose theta to be much less than 1, then this becomes 1, this becomes 1, this becomes, let's call it epsilon. Epsilon, this becomes minus epsilon. So for infinitesimal, rotations, then this guy R now epsilon can be written as the identity plus I times epsilon times some matrix I'm going to call V23, and explicitly this is 1 0 0 0 0 1 1 epsilon minus epsilon. Right? So this matrix B2 here has components in minus I times 0, 0, 0, 0, 0, 0, 1, minus 1, 0. Union. Which is just minus I delta mu 2 delta mu 3 minus delta mu 3 delta mu 2. I mean, you show the same if you rotate it on 2 axis and rotate it on 3 axis, and it is what I asked. Okay, so you can see why then this U2V is a generated vector representation of SOT. It's a nice intuitive interpretation of something that you've seen already before. But then it still begs the question: why am I writing it down this way? Right? Why am I just working with the indices? Yeah. Here's the reason. If I use this intuitive idea of writing down if I use this intuitive idea of writing down this expression here for M mu as this dot product, then I can use the properties of dot products. In particular, the dot product V dot M. Just using the properties of dot products that you're familiar with from high school already, is just V plus M dot V plus M minus V dot V minus M dot M. This is just something that you get from. So basically, you make an expansion of V plus M dot V dot V plus M. Thing is that all of these guys are what we call the quadratic Casimir operators. C2 of V plus M, C2 of V, and C2 of them. They have very specific algebraic interpretation. In fact, these are elements of what, for anybody that's mathematically inclined, these are elements of what I call the universal, of what is called the universal enveloping algebra of the algebra, and they happen to be those objects that commute with all the other generators. Right? In quantum mechanics, again, you've seen this before. This is what you would call L squared, the square of the angular momentum generator. Right? And L squared satisfies a very particular property. L squared commuted with L. And you use the fact that L squared commuted with L to organize your states in the Fock space by angular momentum eigenstates. So all of those states satisfy the property that they were eigenstates in L squared with eigenvalues L times L minus 1 or L plus 1. Right? And you use that to organize angular momentum multiples. And that's what we're going to do in the next lecture.